we're going to cover the module 1b, which consists in the revision of core concept associated with probability theory. So the main reference for this chapter is the book for the class, Probabilistic Machine Learning for Civil Engineer. We're going to cover what's in chapter 3. So probability theory, why would we use it? Okay, there's a famous quote from Pierre-Simon Marquis de Laplace: La théorie des probabilités n'est au fond que le bon sens réduit au calcul. Elle fait apprécier avec exactitude ce que les esprits justes sentent par une sorte d'instinct. So the translation of this is the probability theory is at the end only the common sense reduced to calculus. Okay, it allows to appreciate for the right minds what the right minds feel by instinct. Okay, so this is really the interpretation we're going to use. Okay, here probability theory is going to be to represent common sense using mathematical formulations. Okay, so why would we use probability theory? Okay, the question I usually ask people is, do we want to use probability theory to describe random phenomena? Okay, for instance, if we look at the coin flip, okay, if I flip this coin, will I obtain head or tail? Is it something that is intrinsically random? Okay, the answer to this is no. There are few phenomena that are intrinsically random. Okay, here the coin flip problem might appear to be random simply because I cannot predict the outcome. But it's not because you cannot predict the outcome that something is intrinsically random. Okay, the outcome appear random to you because you don't know the initial position, velocity, angular velocity of the coin when it leaves your finger. However, if you could control all those things, initial position, velocity, speed, acceleration, rotational velocity, and all of this, you could predict with a high certainty what is going to be the outcome. And the proof of that is that there are many even simple machines that can do this. For instance, this is an example of coin flipper with the 95% accuracy. So this is basically just a device that will lead to repeatable condition of initial position, velocity, and speed. And with this, we're going to achieve a really high predictability about what's going to be the outcome of the coin flip. Okay, so at the end, there are very few phenomena that can be considered as being intrinsically aleatory, meaning they're unpredictable. Okay, so here what we want to do. Is to employ probability to describe our knowledge of those phenomena. Okay, and this is what we call epistemic uncertainty, which are related to lack of knowledge. Okay, so for instance, if we take an example of a dam here, if we take one specific point on that dam, so at a given point in time at that location, the Young's modulus here is unknown. Okay, I don't know exactly what's the Young's modulus or the stiffness of the concrete, but it's not because I don't know that Young's modulus that it's necessarily in a random quantity, something that varies. Okay, so the stiffness of the concrete doesn't vary, at least if we consider a specific point in time. Okay, it's a fixed value. It's only that I don't know that value. And here I'm going to use probability theory to describe what is the knowledge I have of that concrete stiffness, for instance. So here the Young's modulus won't vary locally. It's only that we don't know its value. And here we describe our uncertainty about E, that's Young's modulus, using probability. And here what you have to keep in mind is the less we know about something, the more important it is to use probability theory to describe our knowledge. So if we have a quasi-perfect knowledge of something, okay, the difference between treating it as a deterministic quantity or using probability theory, there's going to be a very small gain by choosing one over the other. However, the more uncertainty we have, then we're going to consider all the possible outcome associated with our like weakly informative knowledge. Okay, so the less we know, the more we should model our thing with probability theory. So who or what is using probability theory? Actually, we have in our everyday life so many applications of probability theory. For instance, if you want to launch a rocket, this heavily relies on probability theory. Whatever it has to do with controls and robotics rely on probability theory. Autonomous cars, some voice assistants that can recognize when you're speaking to your phone, this heavily relies on probability theory. If you're doing a query on Google, it finishes your query before you finish typing it. This also relies on probability theory. So if it works for all those everyday life applications, this is also going to work for our engineering applications. So what we're going to cover together today is first the background associated with set theory. Then from this core information, we're going to move into the concept of probabilities. And this is going to give us the framework to then describe what is going to be the workhorse that we're going to use in machine learning, which are random variables. Okay, either in the case of univariate random variables, or in the second case, multivariate random variables. Then we're going to look into the concept of moments as well as expectations. Okay, how can we use it and how do we derive these quantities? And then one key aspect we're going to look at is function of random variables. Okay, because at the end in machine learning, we're going to build complex models. Okay, and we're going to see in many cases these models are function of random variables. Okay, how can we handle these cases? And finally, what happens if these functions are nonlinear? We're going to see how can we linearize nonlinear model for the purpose of being able to analytically handle nonlinear function of random variables. So this is again in our module 1, the second part of our revision, according to the basics of probability theory. So first module, we're going to look at set theory. So what are the definitions associated with it, some examples of applications, and what are the elementary rules associated with set theory. So first, in terms of nomenclature, the definition we're going to use, a set can be considered as an ensemble of events or elements. We're going to refer to either the universe or the sampling space by this calligraphic letter representing a set. Okay, it consists in the ensemble of all possible results. And here we have no limitations. It can be either discrete or continuous, finite or infinite. So in the case of a discrete set, it could be either finite or infinite. In the case of a continuous set, it's intrinsically infinite, because even if we have a bounded interval, say between 0 and 1, there's an infinitely many possible outcomes in that continuous range between 0 and 1. Then we have what we call an elementary event. So this is going to be denoted by a lowercase variable. Okay, it's going to be a single event that belongs to our sampling space S. Then we're going to have the event E. So an event is going to be a set of elementary events. So X is a single outcome. E is going to be a group or a set of multiple outcomes belonging to my sampling space S. So we can say that an event is going to be always a subset, always going to be equal to my sampling space. If we say that my event is equal to the sampling space, it's going to be a certain event. Okay, this thing happened for sure. And on the opposite, if my event is the empty space, it's going to be an impossible event. That thing cannot happen. If we put a bar over an event, we refer to the complement of the event, meaning everything that is in the sampling space, but not in my event E. So all of these things we can represent on what we call a Venn diagram. So this is what we have here. So the whole box is my sampling space S. Each point is going to be a possible elementary event X. So you see that the event E is a collection from multiple elementary events. And whatever is in S, but not in that blue shaded region describing my event E, is the complement of E. So let's apply this to an engineering example. Okay, we want to describe the state of a structure right after an earthquake. So the reality describing the state of a structure is in reality a continuum. Okay, so going from no damage to total collapse. Here, to simplify that context, we're going to discretize this sampling space from no damage light damage, important damage, or total collapse. Okay, we go from a continuum to 4 discrete possible outcomes. And we're going to summarize this by no damage ND, light damage LD, important damage ID, and collapse CO. We can say that I have an event E1, which is going to be ND and LD, so no damage or light damage. So that could be a collection of elementary events. A second event could be simply the collapse. And I can say my complement of A1 is going to be what's in my sampling space, but not in E1. In this case, important damage and collapse. I could say the complement of E2 is going to be anything but E2, so ND, LD, ID. Okay, I'm sure you get a concept. So what are the operations we can do on events? So given a set of n events that belongs to a sampling space S, we can say I want to do the union of events. So union, you can interpret this as a or. So either E1 happen or E2 happen. So the union is represented by this U operator. Okay, so if we represent the two events on our event diagram, the red circle represents the event E1, the green circle, the events E2. So if we want to do the union of E1 and E2, it's everything that is shaded in blue. So where either E1 happen or E2 happen or both happen simultaneously. The other key operation is intersection. Okay, so this is like the AND operation. So it's E1 and E2 happen. And here in terms of nomenclature, we may put that inverted U, that cap symbol, or not put anything at all. So when we don't put anything, it's the same thing as if we would put this symbol. Okay, so both represent the AND intersection. E1 and E2 happen simultaneously. So on our Venn diagram, let's represent that intersection we're having here. So, and this generalized to no matter how many events we can have. So here we have the intersection if E1, E2, E3. So this is the intersection of E1, E2, intersection of E2, E3, intersection of E1, E2, and the intersection of our three events, E1, E2, E3. So if we develop a little more on the rules, the first one is going to be the commutativity. Okay, if I say that E1 union E2, I can permute my events to say it's equal to E2 union E1. Okay, this is the same thing we have for the intersection. We have the associativity rule. So if I have E1 union E2, and I have my parentheses here, so this has priority over E3, but actually I can move my parentheses over by saying I'm going to first do E2 union E3 and then union with E1. This will give exactly the same results, okay? So the union of E1, E2, E3 has no order of preferences. So we can say that we can, in a general way, represent the union for the event EI from I equal 1 to n as the union for all these elements without necessarily having a specific order in which we're going to do these union. So in the case of my tree event E1, E2, and E3, the union is the blue shaded area where we have either of those three happening, either one at a time, two at a time, or three at a time. We have the same thing for the intersection. We don't care about the priority order. We can just generally represent the general intersection for a set of n events as this cap operator from I equal 1 to n of EI, okay? And this represents, in this case, the intersection of all my events. We have the distributivity property, which says that if I have the, in parentheses, E2 union E3, and I want to do the intersection of this result with E1, I can distribute that intersection inside my parentheses to say I'm going to do E1 intersection E2, union E1 intersection E3, okay? So if we look at this, what it would give, if we start by doing here E2 union E3, so we have, sorry, event 2, event 3. So the union of both would be everything we have in one or the other, okay? Then if we want to do intersection with E1, we see that it really gives what we have in light blue here. If instead we want to represent it as the intersection of E1 and E2, so the intersection of E1 and E2 is the part we would have here. The intersection of E1 and E3 would be the part we would have here. And again, the union of both would be what we have in light shaded blue here. In terms of convention, we have to keep in mind that the intersection is going to have priority over union. Otherwise, if you want to represent something else, you have to use the parenthesis to describe that property. So let's look more specifically at some type of event we're going to be interested in. Okay, so in general case, now we're looking at a set of n events belonging to the sampling space. We're going to say that this set of n events is going to be mutually exclusive, ME, if the intersection for the pairwise intersection of EI, EJ is the empty set, meaning there's no overlap for these two events for any I not equal to j. So we don't talk about the event with itself, but any distinct event will have no overlap. So in that case, if we represent this by the Venn diagram, E1 doesn't have any overlap with E2. We're going to say E1 and E2 are mutually exclusive. We could also have events that are collectively exhaustive. So we're going to say that our set of events from E1 to En are going to be collectively exhaustive if the union for my set of n events is equal to my sampling space. So meaning that if I do the union for E1, E2, E3, in this case En, it's going to lead to my sampling space. And then finally, we can have both together. So events that are going to be mutually exclusive and collectively exhaustive. This is what we have on the Venn diagram here. And note that the difference between this Venn diagram and this one is that here we have an overlap possible, because here it's only mutually collectively exhaustive. But here we have no intersection between my events, and the union of all my events makes the sampling space. Another thing you need to keep in mind is that if we take an event, for instance, an event E, and its complement, these two are always mutually exclusive and collectively exhaustive. Now let's move forward with a concept of probabilities. Okay, what is it? We're going to introduce that concept. What are the axiom and the elementary rules associated with probability theory? And then we're going to look into conditional probability and Bayes' rule, which is going to be fundamental for the learning part in machine learning. So if we look at what is the interpretation of probability. So we talk about PR for the probability of an event EI. Okay, so this is how we describe mathematically this concept. So there are two main interpretations of probability. The first one is the Bayesian interpretation. Okay, we say in that case that the probability of an event will quantify the likelihood of that event with respect to all the other events in the sampling space S. And here, the specific characteristics of that Bayesian interpretation is that it depends on our prior knowledge. And that means that our probability can change as we obtain new information. Okay, the probability is, in the Bayesian context, is really associated with that epistemic concept, where it describes our lack of knowledge, meaning that it doesn't represent an intrinsic property of the system. It's really going to represent our knowledge of that system. It means that as we collect new information, it's going to change our knowledge, and in turn, it's going to also change the probability we're describing our knowledge of the events. So the other interpretation of probability is what we call the frequentist interpretation. So in that case, the probability is going to be interpreted as an intrinsic property of what we're studying, and we can see it as a limit as the number of trial tend to infinity of the number of outcome of an event over the total number of trial we've done. And here, what really empowers all the great application we've seen earlier is that Bayesian interpretation, okay, which allow us to refine our knowledge as new data is collected. Okay, what are the fundamental axioms of probability theory that we need to cover to understand what's coming next? First is that the probability of an event is always defined or is always bounded between 0 and 1, okay, including 0 and including 1. So for instance here, if I have an empty set, the probability of the empty set is 0. If on the opposite, the probability of the sample space is always going to be 1. So as we just said, probability of the sampling space is 1 because it's a certain event. The sampling space contains all the possible events. So the outcome is for sure going to be in that set. If we have two events, E1 and E2, which are mutually exclusive, okay? It means that there's no possible intersection. They cannot happen simultaneously. In that case, the probability for the union of event 1 and event 2 is going to be given by the sum of the probability for each event. So for instance, we have two events which are mutually exclusive, no intersection. The probability for event E1 and event E2 occurring, since both cannot occur at the same time, it's the sum of the probability for the event. Okay, there are some rules we can derive from the fundamental axiom we just saw. For instance, we can derive the probability of the complement. So if we know the probability of an event E, the probability of its complement is going to be 1 minus the probability of that event. We have the probability of an empty set is the same thing. The probability of the event, which is the complement of the empty set, is going to be the sampling space. So the probability of sampling space, we saw it's 1, 1 minus 1. The probability of the empty set is going to be 0. We have the general addition rule for events that are not mutually exclusive. In this case, it's the probability for the union of event E1 and event E2, where these two are not necessarily mutually exclusive, is going to be the probability of event E1 plus the probability of event E2 minus the intersection for the probability of both happening simultaneously. And we're going to see through this Venn diagram, where does that come from? So here we have our sampling space, we have here our event E1, and we have our event E2. And we want to quantify what's going to be the probability for the union of E1 and E2, represented here by the light blue area. So the probability of event E1 is defined by my event here. The probability of event E2 is defined by what's in green here. But here, if we calculate the probability defined on this diagram plus the probability on this diagram, we're going to double count what's inside my intersection here, okay? Because when they happen at the intersection, they both happen simultaneously. So that's why, in order to avoid that double counting of the probability included in that part of the Venn diagram, we need to remove one time the probability that is defined over that intersection region. Now we're going to look at a key concept, conditional probability, okay? This is the building block of what we're going to see later on as how do we learn with machine learning, okay? So if I want to define conditional probability, I want to have the probability of the event E1, given that I've seen that the event E2 has happened, okay? Or knowing that the event E2 is happening. So in this case, the vertical bar, what's on the left is what we're going to quantify the probability for. What's on the right is a known thing, okay? So this is the probability of the event E1 conditional on the realization of event E2. And by definition, such a conditional probability can be defined by the ratio of the joint probability of both E1 and E2 happening simultaneously divided by the marginal probability of E2. And this is given, of course, that the probability of E2 is not 0. So we can reorganize these terms to say that joint probability of two events is going to be the product of a conditional probability and a marginal probability. So in this case, if I want to add the conditional probability of E1 given E2 times the probability of what's on the right of the conditional probability of E2. This is going to give me my joint probability of E1 and E2. But there's not only a single way to represent this, because I have two possible ways of describing my conditional here. Either E1 given E2, or the inverse way, E2 given E1. And in this case, it's going to be times the marginal probability for E1. And here, when we refer to marginal probability, we're talking about the probability for a single random variable. Okay, so in this case, if we describe that joint probability of E1 and E2, so it's the probability defined on that intersection on my Venn diagram. So in the case where the events E1 and E2 are deemed as statistically independent, so this is the symbol representing statistical independence, we're going to say that the probability of E1 given E2 is going to be equal to the probability of E1. What it means? It means knowing the value of E1 doesn't change my knowledge. Knowing the value of E2 won't change my knowledge for what could be the value of E1. So it means that in such a case, we can obtain the joint for the probability of E1 and E2, so the intersection, as the probability for the marginal. So probability of E1 times the probability for E2. Okay, so if we want to go one step further, we have to look at the chain rule. How, in a general context, we build joint probability for multiple events. So if I have a set of n event, and I want to describe what is my joint probability for that entire set of events, I can build this using conditional probability. So I can say that the probability of E1 given all the other events E2 from En times the joint probability from E2 to En. Okay, so I broke down that joint in a conditional and a joint. But then I can still break that joint by the conditional of E2 given E3 to En times the joint from E3 to En, okay? And I can keep breaking that until I have n terms, okay? From these n terms, there are going to be n minus 1 conditional probabilities in one marginal probability. So as an example, if we have 3 events, E1, E2, E3, and I want to model that joint probability for these 3 events, I can model this by the conditional probability of E1 given E2 and E3 times the conditional probability of E2 and E2 given E3 times the marginal probability of E3, where this product here is going to give me the joint of E2 and E3, and this is going to give me the joint for E1, E2, and E3. Okay, let's look at what we call the law of total probability. So given we have an event A that belongs to the sampling space. So here the sampling space is my whole box. This blue circle is my event A. And given a set of n events that are mutually exclusive and collectively exhaustive, meaning I have no overlap between these events, and the union of all these events makes my sampling space. So we can define the probability of A using these conditional probability. So we're going to say that the probability of A is going to be the probability of A given E1 plus the probability of A given E2. Probability of A given E1 times the probability of E1 plus the conditional probability of A given E2 times the probability of E2 times the probability of plus the probability of A given E3 times the probability of E3, etc. Okay, it's always the conditional of A given EI times the probability of EI, and I sum over all possible events. And this is the what I have on the right of my summation. This is going to be my joint probability for the event EI and my event A. And by summing over all event EI, this is called the marginalization. Okay, by doing this, I'm building my joint for E and A, and then I marginalize over the event E. So if we continue with this, we can define the union rule. So if we have the probability for the union of event given another event A, we can say it's going to be equal to the probability of E1 given A plus probability of E2 given A minus the intersection of probability of E1, E2 given A. So the same thing for the intersection. The joint conditional probability of E1, E2 given A is going to be equal to the probability of E1 given E2 and A times the probability of E2 given A. And if we represent this in another way, we can say the probability of A given B can be obtained by marginalization, where we're going to say if we sum over all the event EI for the conditional probability of A given EI and B times the probability of EI given B. Where here, what we have on the right of the summation is actually the joint conditional probability of A and EI given B. And then we can marginalize over all the EI if we only want to obtain the conditional probability of A given B. So now let's look at Bayes' theorem, okay? Given we have a set of n mutually exclusive, collectively exhaustive events, and we can define the joint probability of A and EI as a conditional and a marginal, okay? Probability of A given EI times the marginal probability of EI. As we said earlier, we can also express that joint probability in the second way. We can also use the conditional probability of EI given A times the probability of A. So now these two things are equal, okay? So I can represent them in this way. So if I'm looking for the probability of EI given A, I can simply send this on the other side of the equation. It's going to be the probability of A given EI times the probability of EI divided by the probability of A. And in this case, this is what I call, in the context of Bayes' rule, my posterior probability, okay? How much knowing A change my knowledge of the probability of EI. And the terms of the Bayes' rule are what we see here is the likelihood function. Given EI, how likely is it to observe A, times my prior probability for the event EI, divided by the probability of A, which is referred to either as the evidence or the normalization constant, okay? So here's a first introduction to Bayes' theorem. We're really gonna go in depth with Bayesian estimation in module 3. So for Bayes' theorem, if we want to represent this visually on the Venn diagram, if we're looking at the conditional probability of E1 given that the event A occurred, we can say it's going to be the conditional probability of A given E1 times the probability of E1 divided by probability of A. So here the product of the conditional of A given E1 times the marginal of E1 is actually the probability defined over the intersection here, okay? Divided by the probability of A is the probability defined over that thing. So the probability defined over the intersection of the two divided by the whole probability. This is what we have here. And at the end, the probability of A represent actually a normalization constant. So in this case, this is as we've seen before. We can express the joint probability for A and EI times probability of EI. We do this sum over all possible event EI. So this is how we use marginalization in order to obtain that evidence or probability of A. And keep in mind, we're going to see that in more detail in module 3. This is typically for things that are not toy problems, that are real life example, extremely difficult and can be computational, extremely demanding computationally to calculate that normalization constant. Okay, so now let's look at the core of what we're going to be using for machine learning. Okay, all the concepts we saw were there for us to really understand well the concept of random variables. Okay, because in most cases, this is what we're going to be working with when we're going to be building machine learning problems. So we're going to look at several cases: discrete random variable, continuous random variable, what happened with, we have conditional probability with random variables, and finally the general notation for these things. So first, let's define what's a random variable, okay? We can represent what we defined earlier through the sampling space on a line, okay? So we had our sampling space. This is gonna be this line representing the possible values for an outcome X, okay? So each possible elementary event is 1 point on that line. So the sampling space representing all the possible value would be a set, either finite or infinite, on this same line. The collection of elementary events here, so my event E, would be a range on those possible outcomes. So for a random variable, we need to distinguish between the outcome and the random variable itself. So for instance, if I say that lowercase x is a realization of the random variable, okay, so a possible outcome. So in this case, all these values are possible, okay? But here we say that x described by a uppercase is the random variable. So x is a specific value, uppercase is no specific value. Uppercase, which describes the random variable, can be any value within the sampling space, okay? But all those values don't have equal probability. We're going to define that later on. So the probability that a random variable, capital X, take a specific value described by lowercase x is going to be described in the case of discrete space by a probability mass function, PMF, or in the case of continuous domain by probability density function. So if we look first at the case of discrete random variable, okay, we're going to look at probability mass function. So we can describe the probability that the random variable x is equal to a specific value, okay? So here in the shorthand notation, we're going to omit the random variable and just say the probability of x is equal to the PMF of x, okay? So this is a probability for a specific outcome. This is going to be the probability mass function, okay? Here we explicitly represent the variable for which we define this PMF. Depending on the case, if it's already obvious or not, I may or may not put that variable explicitly. But in every case, we're referring always to the same thing here. So this is the probability that the random variable x is equal to a specific value. So the properties here is that the PMF, so the probability for any outcome x, is always defined between 0 and 1. So always greater or equal to 0, lesser or equal to 1. And here, the sum of the probability for all the possible elementary event in my sampling space, so all the possible values of x, must be equal to 1. And this must always be satisfied. And this is because all the events in x are mutually exclusive and collectively exhaustive. Okay, all the events in x have to happen one at a time. So I cannot have 1 and 2 happening at the same time. It's either 1 or either 2. And the union of all the possible events represent my sampling space. So let's put that in the context of application, okay, with our damage structure after the earthquake. So our sampling space was no damage, light damage, important damage, or collapse. So if we want to represent this sampling space on a line, it would be the event 0 would be the no damage, 1 light damage, 2 important damage, 3 collapse, okay? And the height of the stem here represent the probability of each event, where these height are always between 0 and 1. And if I sum the height of each stem, it must be equal to 1, okay? And here, if I want to define events such as the random variable x taking value between 1 and 2. So it's going to be the probability of the event 1 and probability of event 2. Okay, now let's look at continuous random variable. Okay, so now we're going to deal not with probability mass function, but with probability density function. Okay, this is labeled as PDF or probability density function that are going to be described by lowercase f of x. So probability mass function was lowercase p, PDF lowercase f. And here we may or may not refer to the random variable evaluated for a specific outcome x. And here keep in mind the term density, okay? A PDF is not a probability because in a continuous case, there are an infinitely many possible outcomes. It means that the probability that the random variable take one of those specific outcomes is actually 0, okay? So here we can only define the probability for a probability density function over a sliver, okay? Over a little area of my domain. So I want to say that the probability that the random variable x is between x and x plus delta x, this is going to be a valid probability. And we can represent this by our probability density times a sliver delta x. So this is as represented here. In itself, on a point evaluated on that PDF, it's not a probability, it's a probability density. If we multiply the probability density times a sliver delta x, is going to lead to a probability. So here's an example of probability density. And if we integrate this probability density over the whole possible domain for x, so over its whole sampling space, the result must be equal to 1. Okay, because the probability defined over all possibility must be the certain event. And here in all case, the probability density must be greater or equal to 0. In the case of the PMF, the probability mass function, all the probability for each possible outcome must be between 0 and 1. Here, the probability density, be careful, it can have value that are greater than 1. Why? Because at the end, the only thing we need to satisfy as the integral over the whole domain must be 1, okay? And in order to satisfy this, it might happen in some case that the probability density is going to be above 1. Okay, now let's look at the concept of cumulative distribution function, CDF, okay? A CDF is going to be described by uppercase F, and we may or may not refer to the random variable X, and we evaluate that CDF at a specific outcome, lowercase x. And this actually describes the probability that the random variable capital X is lesser or equal to a specific outcome, lowercase x. In the case of a discrete random variable, this represents the summation of my probability mass function for all value x prime lesser or equal to a specific value x that I want to evaluate. So for instance, here I have my PDF, or my PMF, my probability mass function for a random variable x, which can take 4 possible outcomes. So here, if I want to draw my cumulative mass function, or my cumulative distribution function, I'm going to have here the probability that x is lesser or equal to 0 is the same value as the PMF. Then the probability that this one is lesser or equal to 1 is this one. So I'm going to sum the height of the stem plus the previous value of the CDF I had. Here, I'm going to take this value plus the height of the stem. I'm here, the current value plus the height of the stem. And at the end, the probability that I'm lesser or equal to the highest possible output is always equal to 1. So now let's look at the same thing, but now for the continuous case, or for the discrete case, it was a sum. For the continuous case, now it's an integral, okay? So I'm going to integrate my PDF from minus infinity to a value x prime, okay? So this is going to lead to something, a function that is non-decreasing, that goes from 0 to 1. Why is it non-decreasing? Because we are going to integrate something that is strictly positive. Okay, so we're always adding something. So there's no case where this function can go down. It's always non-decreasing. And in every case, whether we are in the discrete or continuous case, the CDF evaluated at the lower bound is going to be 0, upper bound always going to be 1. Okay, so what is the link between a PDF and a CDF? What is the relationship between one and the other? So in the case of a continuous random variable, we can see that the CDF is the integral of the PDF. So the opposite is also true. We can say that the PDF is actually the derivative of the CDF. In the case of discrete random variable, the PDF is actually the difference between the CDF value between two consecutive outcomes. So here we're only seeing an overview. We're going to see in greater detail in module 2 what are the common PDF and CDF family that we're going to use in this course. So for now, just a quick overview. We're just going to see the univariate normal random variable. Okay, so when we describe the probability density function for a random variable, we're going to use that mathematical nomenclature. So we say that the random variable x, this tilde symbol reads like distributed like, okay? This is a normal for this defined for the possible outcomes, lowercase x, and that semicolon indicates what's on the right of it, what are the parameters of that PDF. In this case, mu, the mean, and sigma square, the variance, okay? So here we have the probability density function. This is the analytical formulation for the normal PDF for one random variable x, okay? So the PDF is 1 over square root of 2 pi sigma, exponential of minus 1/2, in parentheses, x minus its mean mu, divided by standard deviation sigma, all of this square, okay? And if we want to describe the CDF, it's going to be the integral of this PDF from minus infinity up to x. So there's a dx missing here. And if we want to represent it visually, how does it look like? Here I have my PDF, here I have my CDF. You see that this apex of my PDF is at the expected value. And here we have the mean plus and minus 1 standard deviation that will correspond to the inflection point we're seeing here. In the CDF, we have the same thing, the midpoint where the probability of 0.5 is the mean, and have plus and minus 1 standard deviation. So we're going to come back in greater detail about this in module 3. So now let's look at how can we define conditional probability and random variables, okay? So let's consider we have an event E and a random variable X, okay, capital X. So we say that the probability of the event E conditional on the realization for the random variable X equal to a specific value is going to be described by the probability of the event X given the other event X, the random variable, equals to a specific value, okay? We can represent this by the probability for the intersection of the event and the two events. So the event E and the outcome for the random variable equal that specific value, divided by the event that the random variable take the specific value, okay? So here we can actually, when we're going to write it down, we're never going to write it in that long form, okay? We're going to drop these brackets, and actually we're going to go even further. We're just going to say that joint probability here, so probability of the intersection, can be broken down into a conditional, so probability of the event X given the event E times the marginal probability of the event E, okay? And in the common usual form, we're even going to drop this and we're just going to write it this way. The probability of the event E given we have observed X is going to be the probability of X given E times the probability of E divided by the marginal probability of X. Okay, so if X is a discrete random variable, we can express the conditional probability of the event given X as probability of event given X is going to be the PMF, the probability mass function of X given E, times the probability of E divided by the PMF of X. So if we want to reverse this, the probability of X given E is going to be the, so whether or not we put the subscript here is the same thing. Here it's because we want to explicitly refer to the random variable. Here we didn't, but it means the same thing. So this is the probability of this event. Here we're referring explicitly to that PMF. So it's going to be the probability of event conditional on X times the marginal probability of X divided by the marginal probability of the event. So whenever we have probability, we're referring to a specific event. Whenever we have that lowercase p, we're referring to a probability mass function. So if uppercase X is a continuous random variable, so in this case, the conditional probability of the event given the outcome X is going to be a function not anymore of a probability mass function, but this time of a probability density function for X given E times the probability of the event divided by the marginal probability density function for my event X. If we want to reverse that condition, so in that case, we would be seeking not a probability for an event, but what is going to be the posterior probability density for X, knowing that the event E has occurred, is going to be the conditional probability of the event given X times the PDF of X divided by the marginal probability for the event E. So if we look more closely at the notation for a random variable, when we describe a probability, so probability of X is actually in the long form, the probability that the random variable uppercase X equal a given outcome, okay? So the random variable here, we're gonna say a random variable is always distributed like a given either PDF or PMF, okay? And we may or may not refer to the random variable explicitly, okay? Depending on the context, if it's clear, I might omit it. If it's not clear, I'm gonna specify it. And we can also further refine that notation by implicitly, as here, or explicitly, as here, referring to the parameters of my PMF, or more specifically here, PDF, okay? So most probability density functions are parameterized by some parameters, okay? And we might, in some cases, want to represent explicitly those parameters. When we want to do so, we add a semicolon here to represent here on the right of those semicolon, what are the parameters of that PDF. On the left of the semicolon is going to be the variable for which the PDF is defined. In a case of, for instance, a normal random variable, we're going to say the random variable x is distributed like a normal with mean and standard deviation. So this is one possible notation. A second one is one where we really distinguish between the variable, so the possible outcome of x for which the normal is defined, and its parameters on the right. So either can be used depending on the references you're consulting. We have the same thing. This is for a continuous case. For a discrete case, we have the PMF with or without reference to the random variable, and with and without dependency on the parameter for the PMF. And finally, for a conditional random variable, we're going to say the random variable x condition on the outcome y. Okay, this is going to follow the PDF of x given y, where we might or might not have that dependency explicitly on the variables as indices. Okay, so when we're going to be looking at machine learning problems, there are going to be many quantities that are going to be involved. Okay, and that requires for now to define the concept of multivariate random variable. Okay, with multivariate random variable, we're going to need to define a concept of probability density function in multivariate domain. Same thing for conditional probabilities. So let's consider now multiple phenomena. Okay, multiple phenomena, their joint outcome is going to be described by a multivariate random variable. So my x-pole describes a vector of random variable. Okay, so in this case, I have a vector of n random variable. So it's always vector, just as we described before, it's always a column. And the lowercase x-pole is going to be a vector describing what are the possible outcome of that random vector. Okay, lowercase, it's the outcome, uppercase is the random variable. So this is a specific value. This is all the possible value as defined in the sampling space of my random vector. So here at the end, what you have to keep in mind is that random vector describes the simultaneous realization from several phenomena, okay? And this is going to be key for later on creating our machine learning models. So if we have the multivariate probability mass function, PMF, is going to be P of now a bold vector of random variable evaluated for a vector of possible outcome. This represents the joint probability for the intersection of many outcomes. So the random variable x1 is equal to a specific outcome x1, x2 equal to a specific outcome x2, up to xn equal to a specific outcome xn, okay? And again, the joint probability for these multiple events is always bounded between 0 and 1. So it's always greater or equal to 0 and lesser or equal to 1. So here, if we have a joint PMF for variables x1 up to xn, and I sum over possible outcomes of xn. In that case, this is the operation we call marginalizing. Okay, if we marginalize that joint PDF, we're going to be left with the joint PDF for all variable except xn. So if we would have sum on the possible outcome, not of xn, but f xn minus 1, is going to be the joint of all variable, but xn minus 1. So if we do that marginalization over all possible dimensions, okay? In that case, if I sum my joint PDF over all possible x1 up to xn, then this result should return 1. If it's not the case, there's something wrong with your calculation, okay? Because the sum over all possible outcome must always be 1. And at the end, when we're referring to the probability of a single random variable, we're referring to a marginal PDF, okay? A marginal PMF for a single random variable. Okay, let's put this operation of marginalization in application. So let's assume we have two random variables, x1 and x2. And here, as we've seen before, this symbol implicates that or implies that x1 is statistically independent from x2. So this is my PMF for x1. So I have a probability that x1 equal 1 equal to 0.1. Probability that x1 equal 2.5, probability that x1 equal 3 is 0.4. So keep in mind, if I sum over all the probability for all possible outcome, it must give me 1. And here it indeed gives me 1. I have the same thing for the marginal probability of x2 for each of the 3 possible outcome of x2. Now, if I want to build the joint for both x1 and x2 occurring, I can build that joint by taking the product of the marginal, okay? And this is what I represented here on this joint probability mass function. So this is the axis for x1. This is the axis for x2. So what do you see on the back of the graph here? The stems, the height of each stem, represent the marginal probability for each possible outcome of x1. This represents the marginal probability for the outcome of x2. And if we take the product, like the height of this bar is actually the height of this bar times the height of this bar. And this is what we do for all of these. So if we want to represent numerically what is the height of each of those bar, it's going to be given by this table where these represent the product of 2 marginal probability. So in that case, if I take this and I sum, for instance, each line is for x1, each column is a value or an outcome of x2. So in that case, if I sum over all possible value of x2, so 0.08, 0.015 plus 0.005, the result is going to be 0.1. I do the same thing for the value of x1 equal 2, same thing for the value of x1 equal 3. And if I look at the result I'm obtaining, if I marginalize my joint PMF with respect to x2, so I sum for the values of x2, I obtain here the marginal PMF for x1. And we see that this is equal to my initial result I had obtained. Okay, so we can always build the joint and then reobtain the marginal by summing over the possible outcome to remove the effect of the random variable. Okay, now if we switch to the continuous case, let's look at multivariate probability density function, so multivariate PDF. So if we want to define a probability for a PDF, it has to be for a certain area, okay, or volume or hypervolume if you're in a higher dimension. But in this case, if we take the product of the PDF times an area delta x, or a hyper area, it's going to be the probability defined for the random variable being between x1 and x1 plus delta x1 intersection up to xn being in the interval xn and xn plus delta xn. So here you have to keep in mind that just as it was the case for the one dimension, in multiple dimension, the joint PDF must be always greater or equal to 0. But as before, it can be greater than 1 because here it must satisfy that the integral of the joint PDF for all the dimension from minus infinity to plus infinity must be equal to 1. The operation for the marginalization for a joint PDF is analogous to what we have defined in the discrete case, meaning that if I have a joint PDF defined for x1 up to xn, if I integrate with respect to the nth variable, then I'm going to obtain the joint PDF for all variables except for the one for which I integrated. And if, as I said just earlier, I integrate for all dimension for all the possible domains, the result must be 1. And I'm referring to the marginal PDF for the PDF of univariate random variables. So let's look at a simple example of multivariate PDF. In this case, we're going to look at the bivariate normal PDF. So this here would be the formulation for that bivariate PDF. This is the part that is controlled by my first random variable x1. This is the second part that controls the variable x2. This controls the dependency between x1 and x2. And this, we're going to see later on, is actually a normalization constant. But here at the end, we're going to come back in detail in module 3 about this. Right now, what I want you to keep in mind is that if we have two normal random variable x1 and x2, The joint PDF is a function of 5 parameters: the respective mean value or expected value for each random variable, the respective standard deviation, as well as rho, the correlation coefficient between x1 and x2. We're going to come back in a few moments here when we're going to talk about what is the correlation coefficient. So now if we want to represent visually how does this bivariate PDF looks like, we have those 5 parameters that are allowing us to build the mean vector and the covariance matrix, where in the mean vector I concatenate the respective mean value for each random variable. In my covariance matrix, each term here on the main diagonal will represent the variance of each variable, and the off-diagonal term are going to be the correlation coefficient times the respective standard deviation, okay? And in the general case, the multivariate normal random variable is parameterized by this mean vector and that covariance matrix. So if we take a look visually at this would be an example. What we have here is a joint PDF for a mean value for x1 and x2 being 0, standard deviation of x1, 2, standard deviation of x2, 1, and a correlation coefficient of 0.6. So these two graphs represent the same thing. So what we have here is the joint PDF represented as a surface. Here it's represented as a contour, okay? But both carry the same information. And what we see here in red are the marginal probability. So this is the marginal probability for x1. This is the marginal probability for x2. And note here that the height of the joint is not the same height as the marginal. Why? Because the joint itself has to integrate to 1 over the whole area. This marginal for x1 has to integrate to 1 only for x1. This here is a little higher because you see that it has a lower standard deviation. So it has also to integrate to 1 over all possible value of x2. So again, we're going to come back to this in detail in module 3. Okay, now I just want you to have an overview over this. So now let's look at what is the multivariate continuous CDF. Okay, so my CDF in the multivariate case is the probability that x1 is lesser or equal to x1, intersection up to xn lesser or equal to xn. And that CDF is again always defined between 0 and 1. And one interesting property with the CDF is that if we evaluate for any dimension at the lower bound, so minus infinity, it's always going to be equal to 0. And on the opposite, if we evaluate for all dimension at plus infinity, it's going to be equal to 1. And finally, we can use that CDF to represent the operation of marginalization. Because if we have a joint CDF for x1 and x2, and evaluate one of those variables at the upper bound, plus infinity, the result is going to be the marginal CDF for the other variable. Okay, and we can do this generally, not only in the bivariate case, but for any cases. And if we want to represent my joint CDF, is going to be equal to my CDF, for which I integrate for x1 up to xn, each from minus infinity up to the value x1 up to xn. And at the end, so we obtain the joint CDF by integration. We obtain the joint PDF by differentiating my joint CDF. Okay. Now, if we want to visually represent that joint CDF in the bivariate normal case, so it's going to be obtained by integrating from minus infinity up to x1, from minus infinity up to x2, with respect to the x1, this should be y, it should be x2, my bivariate normal PDF. Okay, if we look at this, this is the result. So that surface and that contour represent the same thing. This is my joint CDF. And what you see on the back in bold red would be my marginal CDF for x1 and for x2. As was the case for the bivariate normal PDF, this is the bivariate normal CDF. We're going to come back in detail about this in module 3. Okay, so let's make a little wrap up of conditional probability in the context of multivariate random variable. So let's assume that xi is a discrete random variable. And we can define the joint probability, for instance, of x1 and x2 as a conditional and a marginal. okay? And we have two ways of representing a conditional and a marginal, either x1 given x2 times probability of x2, or probability of x2 given x1 times the marginal probability of x1. And that allows us, if we reorganize these terms, to express that conditional probability. So the probability of x1 given the outcome x2 is going to be this conditional, so x2 given x1 times probability of x1 divided by the marginal probability of x2. We can, if we're interested in the conditional PDF or PMF of x2 given x1, we simply swap the terms, okay? So if we have a special case where x1 and x2 are statistically independent, okay? So in that case, we can represent that conditional probability of x1 given the outcome x2 as simply the marginal probability of x1. Because if x1 and x2 are statistically independent, it means that knowing x2 won't change my current knowledge of x1. Okay, so I might as well represent this conditional probability by the marginal probability of x1. If I have a set of random variables from x1 to xn, and they're all statistically independent, it means I can represent their joint probability by the product of their marginal PMF. Okay? In the general case, the random variable you're going to consider for a machine learning model are most likely not going to be statistically independent. So in that case, if you want to build the joint PMF in the general case, you're going to use the chain rule we saw earlier, meaning you build that joint by the n-1 product of conditional PMF and one marginal PMF or probability mass function. Yeah. And here, keep in mind that the order in which you create these conditional will lead, no matter what is the order, you will obtain the same result at the end. So if we look at a simple example with 3 random variables, we want to obtain the PMF for x1, x2, x3. We can break that down into the conditional probability of x1 given x2 and x3 times the probability of x2 given x3 times the probability of x3, okay? And the product of all this is going to be my joint. And now I've described this for probability mass function. If we want to extend this to continuous random variable, keep in mind it's exactly the same thing, okay? All the concepts are the same. We just replace that lowercase p by that lowercase f referring to PDF. Okay, now let's dig into the concept of expectation and moments. Okay, so the first thing we're going to look at moments of order m. We're going to define this concept. Then how can we use these moments of order m to define the concept associated with variance, covariance, and we're going to use this to look at what is the matrix notation associated with the variance and covariance matrices. So when we talk about an expected value, okay, the definition of what is an expected value is going to be the sum of all possible outcomes weighted by their probability of occurrence. Okay, so this operation E with a kind of special font is going to be my expectation operator. The expectation is always defined for a random variable. The expectation for a scalar is a scalar itself. Okay, so we're really interested in the expectation for random variable, which is going to be defined in the continuous case as the possible outcome times their probability density, and we're going to integrate this for all possible values of x. Okay, this represents the sum, in this case the integral of all possible outcome weighted by their probability, and in this case probability density of occurrence. In the discrete case, the expected value of x is going to be a sum, because we have discrete quantity, of the outcomes times the probability of that outcome. And here the interesting property of the expectation is that it's in the linear operation, meaning that if I want to do the expectation of x plus y, where x and y's are random variable, I can as well do the expectation of x plus the expectation of y. So now let's look into the concept of moment. Okay, let's define the moment of order m as the expected value of x to the power m. So it means, if I translate that to the concept we've seen in the previous slide, the expectation of x to the power m is going to be the integral from minus infinity to plus infinity of x to the power m times its probability density, okay? So if m equal 1, it's going to be equal simply to the mu x, okay? It's going to be the mean as we commonly refer to, okay? So this, in terms of engineering, the intuitive interpretation you can have of this this mean is going to be the center of gravity of a cross section. So imagine you have a beam with a given cross section. If you want to balance that beam on your finger, you need to put your finger on the center of gravity of that beam. Here it's the same thing for a random variable. If you would want to balance the probability mass function or the probability density function of your finger, you should put your finger on the expected value, okay, the center of gravity. Then if we take the moment of order 2, so it's going to be the expected value of x squared, okay, the expectation of the square. We don't really care for now about this, but we're going to generalize this into the centered moment of order n, okay? So it's going to be the expected value of x minus mu x to the power m, okay? So in that case, if we generalize what we did before, the expected value of x minus mu x to the power m is going to be x minus mu x to the power m times the PDF of x. And we integrate this over all possible values of x. So for the moment of order 1, the centered moment of order 1, it gives 0. The centered moment of order 2, this is what's actually defining the variance of x. And the variance symbolically is going to be sigma x squared, where sigma x is the standard deviation, sigma x squared is going to be the variance, okay? And in the same analogy we were using before, we said that the center of gravity of a cross-section is going to represent its expected value. Now its variance represents the inertia of that cross-section, okay? So for a beam, the more the material is spread over space, the more the inertia of the cross-section for that beam. Here it's the same for probability density, okay? The higher the variance, the more the probability content is spread over the possible outcomes. The smaller is the variance, the less spread I have in the possible outcome, okay? Same concept as for the cross-section with center of gravity and inertia. So if we look a little more closely at variance, so we can define it as sigma x squared, so this is the same thing as the variance, and we can rewrite this as the expected value of x squared minus the expected value of x to the power 2. That identity is often useful to derive probabilistic quantities. So at the end, as I already mentioned, the variance of x is going to measure the dispersion of my probability density function, and this concept is analogous to the concept of inertia for a cross-section, okay, in the context of, for instance, solid mechanics. And the square root of the variance is represented by here my sigma x standard deviation. Another quantity that is often referred to in the literature is going to be the coefficient of variation. So delta x is defined as the ratio between sigma x and mu x. Okay, this is my coefficient of variation. And this is an adimensional dispersion matrix, okay? So here it represents how much variability I have as a function of my expected value. And in this case, this is going to be defined, of course, if mu x is different from 0. In other terms, we need to look at is the covariance, okay? The covariance represents the expectation of the random variable x minus mu x times y minus mu y. Okay, now we're referring here to the covariance between x and y. So this covariance is defined as I described to you earlier, and we can rewrite this as the expectation of x times y minus the expectation of x times the expectation of y. And here, a key concept we're going to deal with in machine learning is the correlation coefficient, okay? That correlation coefficient helps us to model the linear dependence or to quantify the linear dependence between a pair of random variables. So if I have x and y, two random variables, sigma xy is going to describe the linear dependency between these two. And that correlation coefficient, by definition, is going to be the ratio of my covariance for x and y as defined here divided by the respective standard deviation, so the square root of the variance for each variable x and y, okay? And by definition, my correlation coefficient is going to be defined as being greater or equal to -1 and lesser or equal to +1, okay? Here's an example of data that would have some linear dependency, okay? Here we're related here the husband age in a couple to a wife's age in a couple. So let's be more inclusive. It doesn't have to be a wife and a husband. It could be two person in any couple, okay? So we know that when one person in a couple is older, the other person in the couple is also highly likely to be older. So this is not necessarily a strict rule, but we can see that there's a linear dependency between the outcome of one member of a couple and the other member of a couple, okay? So this is a concept that we can describe with the correlation coefficient. So here's our bunch of examples where you can see correlation coefficient. So in that case, we have a correlation coefficient of 0. It looks like a perfect circle, okay? 0.4, 0.8, here we have +1, and -0.4, -0.8, -1. So we see that if the correlation coefficient is positive, it means when one is high, the other is high as well. When it's negative, is that when one is high, the other is low, okay? And here, these examples are for sigma I and sigma j of equal magnitude, okay? Here, what we have is a perfect correlation or almost perfect, but with sigma I and sigma j taking different value, okay? In that case, sigma for the horizontal axis is high, for the vertical axis is low. So same here, and as we go to the extreme case, we go with two equal value. So here, what we can say is that if x and y are statistically independent, as represented here, it implies that my correlation coefficient is going to be equal to 0, because my data is going to look like a point cloud like this. If, on the opposite, my correlation coefficient is 0, it doesn't imply that my x and y are statistically independent, okay? Statistical independence force my correlation coefficient to be 0, but the opposite is not true. A 0 correlation coefficient doesn't force me to have no dependency, so to have statistical independence between x and y. Why is that? It's because my correlation coefficient only describes my linear dependence between random variables. So in cases like this, I have nonlinear dependency between my two variables, okay? In all of those cases, my correlation coefficient is still 0. Why? Because these dependencies are not linear, okay? What do I mean here by dependency? For me, you should understand dependency as if you know the value of one possible outcome, it informs you about the value of the other possible outcome. So if I know that, for instance, for the first axis that is horizontal, the value is low. So it tells me about what could be the outcome for the second value, okay? Knowing about one outcome, change your knowledge for the other outcome. So in the case of these linear dependency, it's possible to quantify it with the correlation coefficient. In the case of nonlinear dependency, we cannot do that anymore. Another thing we have to take into account is that correlation is not the same thing as causality, okay? The classic example for this is the flu virus, okay? Typically, we see a lot more flu viruses during the winter, okay? So we might be thinking that the cold is causing the flu, but no, actually, flu is a virus, okay? It's the prevalence of the virus in the environment, which survive better in cold and dry climate, that makes it we have way more flu virus cases during the winter, okay? So it's not the cold that caused the flu, okay? So it's not because two phenomena are correlated, okay? So for instance, we have more case of flu during low temperature season, okay? So there would be a negative correlation between the number of flu case and temperature. However, it's not because we have correlation that one is causing the other, okay? In that case, is the greater prevalence of the flu virus that increased the number of flu cases, not the cold itself. So always keep in mind, correlation and causality are not the same thing. Okay, so let's dig a little deeper into the matrix notation, notably associated with that correlation matrix, okay? Given that we have a vector of n random variable, okay, where we know we have a mean vector described by the respective expected value for each of my random variable, okay? And I also have a matrix dx, which is going to be my standard deviation matrix. That matrix is going to be a diagonal matrix, which is going to be only have a non-zero term on the main diagonal, which are going to be the marginal standard deviation for each of my random variable. Then I'm going to have Rx, which is going to be my correlation matrix. Okay, that matrix contains all the possible entries for my pairwise correlation for all my random variable. Okay, so on the diagonal, we can consider that a random variable is always linearly correlated with itself. So it means that on the diagonal, all the terms are always going to be 1. The off-diagonal terms are going to be the correlation coefficient for each possible pair of random variable. And at the end, my covariance matrix, sigma x, is going to be modeled by my standard deviation matrix times R times D. Okay, D times R times D is going to give me that correlation matrix, where on the main diagonal, I'm going to have my variance term for each respective random variable, and my off-diagonal terms are all going to be the same thing, the product of the correlation coefficient times the product of the respective standard deviation. Okay, now let's look into function of random variable. Okay, we're going to look how do we define those and what is the rule that we can apply for function of random variable. So let's consider deterministic function g of random variable x. Okay, so we have a vector of n random variable, which are described by their joint PDF f of x. Then we have a vector of output, described by a vector of m random variable. Okay, so we have n input and m output. Okay, and here we can say that we have a multivariate deterministic function that takes x as input, and even if j is deterministic, if I have a deterministic function of random variable, by definition the output is also going to be a random variable. Okay, and I can rewrite this simply as a vector of univariate function that all take the same input, that vector of random variable x. And the question we're going to answer together is, what is the joint PDF for y, given that we know the deterministic function and we know the joint PDF for x. Okay, and here we're going to be interested in 3 specific cases: m equal n equal 1, so meaning 1 input, 1 output; m equal n greater than 1, so n input, n output; and the other case where m equal 1 and n greater than 1. And what we're mostly focusing here is going to be linear function. So function of the type ax plus b, where a is a constant, b is a constant, and x is a random variable. So first case, we're going to look at the univariate case, 1 input, 1 output, for a function y equals ax plus b. Okay, so in this case, what we have to look at is that we need to maintain the probability constant in the x space and the y space. So that allows us to write that relationship, so that the PDF of x times the sliver dx must be equal to my PDF for y times the sliver dy. Okay, this is what we have here. So we have my sliver dx for my PDF x. This is my function y equal ax plus b. And if I project that sliver through the function on my space dy, I have my neighborhood dy here. So if I want to isolate my PDF for y, I can send that dy dx on the other side of the equality. So that I can say that f of x times the absolute value of dx dy is going to be equal to that PDF for y. Okay, and here I'm going to take the absolute value because the PDF must always be strictly positive. So if my derivative here would be negative, I still have to maintain the positivity for that PDF. So that's why we take the absolute value. So if we take a function y equal ax plus b, where a is a constant, b is a constant, and both x and y are random variable, my dy dx is going to be equal to the absolute value of A. So in that case, I can directly obtain what is going to be the expected value of Y, given that I know the expected value of X is going to be directly my function evaluated at mu X. So in that case, A mu X plus B. The standard deviation of Y as a function of the standard deviation of X is going to be the absolute value of A times sigma X. Okay, let's dig a little more into detail of how do we obtain these quantities. Okay, we're going to look at the case where we say that a function is Y equals to X. Okay, we know the PDF of X is going to be an expected value of 10, standard deviation of 5. And we're looking what's going to be the PDF for Y. Okay, this is the analytical expression for my PDF of X. And I know that dy dx is going to be the derivative of that function is going to be simply 2. So my transformation from the X space to the Y space is going to be f of Y equal f of X times in absolute value dx dy, where dx dy is the inverse of dy dx. So basically, it's going to be my PDF of X evaluated for X, which is equal to Y over 2. So I replace X by Y over 2 times 1/2. Okay, why do I do this? Because here I want to obtain the PDF of Y. So I need to express and evaluate here as a function of Y. And times 1/2, because this is inverse of dy dx. So if I replace X by Y over 2 in that PDF, and I divide that PDF by 2, I'm going to get that formulation. And if I just reorganize the terms, I'm going to have this. So I'm going to have that factor 2 coming here in front of the mean, and the factor 2 coming in front of standard deviation. And we see this still have the form of a normal PDF, where the expected value is now 2 mu X, and the standard deviation is 2 sigma X. Okay, this is how we obtain the formulation we saw in the previous slide. And if we look visually, how does it look like? What I have here is my marginal PDF for X. What I have here is the marginal PDF for Y. This is mu X. And if I project mu X, the expected value on my function, I will obtain mu Y. If I have here in pink, the expected value plus and minus 1 standard deviation, if I project this confidence interval on my function, which is Y equal to X, I'm going to have my mean plus and minus 1 standard deviation sigma Y for my Y space. Okay, how can we generalize this in multivariate domain? So in that case, I have x1, x2 going to y1, i2. And the mapping between my x space and the y space is given by my deterministic function, g of x. So in that case, I still need to maintain my probability constant, but in this case, not over a sliver delta x, over an area delta x, okay? But I can still equate the same thing, f of x dx equal f of y dy. So if I want to isolate f of y, I can say it's f of x times dx dy. So in that case, I would need to express what is dx dy. And to do this, we need to define a new quantity, which is that j, okay? J is going to be our Jacobian, okay? And the kth and ith term in that Jacobian is the partial derivative of yk with respect to xi. And at the end, that Jacobian for the partial derivative of y with respect to x is going to measure the size of the neighborhood for dy with respect to dx. And that Jacobian is actually going to be a square matrix, okay? Not necessarily square, but it's going to be a matrix where this all contain the partial derivative of y, of each y, organizes all lines, with respect to each x organized at each column, okay? So we can see that each line in my Jacobian matrix is like a gradient vector, which is in fact the partial derivative of the first output of my function with respect to all x. The last column is going to be the derivative of my last output for my function with respect to all x. So at the end, my dx dy I'm looking for here is going to be the inverse of the determinant of that Jacobian containing the partial derivative of y with respect to x, okay? And the inverse in absolute value. And dy dx is going to be simply the inverse of this. So at the end, what we're looking at is analogous to what we had before. we're looking for f of y being f of x times, in absolute value, the inverse of the determinant of the Jacobian of y given x. Okay, so if we look for the second case where m equal n and is greater than 1, for which we study a linear function of the type ax plus b, where now x is a random variable, y is a random variable. So my deterministic function is defined by A, which is not a matrix, but a deterministic matrix, and B, which is a deterministic vector. Okay? So my random vector x goes from x1 to xn. It's defined by its mean vector from mu x1 to mu xn, and its covariance matrix, okay, containing all the variance on the diagonal and the covariance terms on the off diagonal. And things that I didn't mention before, covariance matrix is always symmetric, okay? So here I can rewrite this equation with all the terms explicitly represented as being y, my output, is n by 1, this is going to be a random vector, is equal to a matrix A, which is deterministic, it's a n by n matrix, and x would be a n by 1 matrix, okay? This is my random input vector, and B is a n by 1 vector. And in this case, if I have a linear function, what I described earlier as my Jacobian is directly defined by my A matrix. Okay, my A matrix is my Jacobian. So here, if I want to define the mean vector for my output y, in the case of a linear function, is going to be my function evaluated at mx, so A times mx plus b. My covariance for y is going to be A times sigma x times A transpose. So in this case, this is going to be equivalent to the Jacobian times sigma x times Jacobian transpose. Okay, third case we're going to look at, what if I have m equal 1, so one input and several output. Okay, for again, the same thing, we're going to have a linear function of a random variable. So I have n inputs and 1 outputs. So in this case, x is a random vector described by its mean vector and covariance matrix. And I can say my output y is going to be a vector of deterministic constant. So in this case, this is going to be equivalent to the gradient vector of my output with respect to each input times my random vector times a scalar representing b. So in that case, I can say that my mean value for y is going to be A transpose times mx plus b. Sigma y, so the variance for y is going to be the gradient for x. So in this case, it's going to be A transpose times sigma x times A. Okay, where, keep in mind, my gradient vector is the partial derivative of my function with respect to each of my input. Okay, so now what happened when g of x is nonlinear? Okay, because in many cases, you're going to be left with functions that are nonlinear dependency between input and output. Okay, one simple trick we can do here to maintain the analytical tractability we've seen here is to linearize. Okay, so we're going to transform that nonlinear function g of x as a function ax plus b. Okay, how do we define this? Through Taylor series to define here first order approximation. Okay, so let's assume we have a nonlinear relationship between x and y, and we know the PDF f of x. Okay, so we want to define what's going to be the PDF f of y. So in that case, if we don't want to apply the change of variable rules that we've seen earlier, we want to have an approximation that's going to be quick. What we're going to do, we're going to linearize our function at the expected value for x. Why? Because we want to minimize our approximation error. So we want to linearize at the point where we have the highest probability content. In the case of a normal, it's going to be at the expected value. So we calculate the gradient of our function at the expected value in the x space. So in that case, I'm going to replace my nonlinear function in green by that linearized function in red. And I'm going to use the same rules we derived earlier for linear function. Okay? And this is called a Taylor series developed around the expected value. So given that I have a nonlinear function y equal g of x, I can say that I'm going to represent this as an approximation, as y is approximately equal to the gradient of my nonlinear function evaluated at the mean vector times x, the random vector, minus its expected vector. And note that for a nonlinear function, whenever you want to linearize at different point, you need to recalculate the gradient or the Jacobian, okay? Because since the function is nonlinear, for a linear function, the gradient or the Jacobians are constant over the space. In the case of nonlinear function, you need to linearize exactly at the quantity you're interested in this case, always at the expected value. So here, if we want, there was a part missing here. So here, our approximation, I miss it, is going to be the function evaluated at the expected value plus the gradient times x minus its expected value. And this is what we call a first order approximation. Okay, but we can go in higher order approximation. We can add the second order derivative that are going to be contained in the Asian matrix. Okay, the Asian matrix is analogous to the Jacobian. Jacobian was a matrix that was containing all the partial derivative for each output with respect to each input. Okay, the Asian is the same thing, but for the second order derivative. Okay, the derivative of the output with respect of each pairs of input for the second order derivative. And now we have this, which represent the quadratic terms. This would be a second order approximation. We can generalize this for the nth order approximation. For the sake of what we're going to use here, we're going to limit ourselves to the first order approximation. So we're going to say we're going to approximate that nonlinear relationship by something that is linear, ax plus b. Okay, so if we want to summarize the calculation for the first order approximation centered on the expected value, where we're going to linearize our function of m of x, our linear function is going to be of the type g of mx, so the function evaluated at the expected value plus the gradient evaluated at the expected value times x minus the expected value. So it means from this, I can analytically calculate what's going to be the expected value of the output as simply the function evaluated at the expected value for x. The variance for the output is going to be the gradient vector evaluated at mx times the covariance for x times the gradient transpose. Where here, keep in mind, gradient is the partial derivative of my output with respect to each of my input. So if we wrap up what we've reviewed together, so first, probability are there to describe our knowledge, okay? They're not going to be interpreted as an intrinsic property of a system, okay? They really describe our knowledge as that system. And that involves that the more information we collect, the more it might change our estimate for the probability, okay? This is not something that is fixed in space or time. And the less we know, the more we should employ probability theory, okay, to describe that lack of knowledge we have about the phenomenon we want to consider. Then most of the development we're going to do in the next module are based on that Bayesian interpretation of the probability, okay, where the probability of an event quantify the likelihood of the event with respect to other possibilities. And again, as I said, as we collect new information, these probability are going to change because our knowledge of that event is going to change. We've seen many operation, intersection, union. This means it's part of a set, it's part or equal of a set, or it belongs to a set, okay? Now, so it's contained in a set, contain or equal, and it belongs to a set. We've seen fundamental axiom, so a probability is always greater or equal to 0, less or equal to 1. The probability for the sampling space is always 1. If two events are mutually exclusive, the probability for the union is simply the sum of the probability for each event. In the general case, if we want to describe the probability for the union of event, we have to use the inclusion-exclusion rule, where we're going to subtract the joint probability for the intersection of event. So in the case of two events, the probability of the union of U1 and U2 is going to be the sum of the probability for event E1 plus probability of event E2 minus the probability of both events occurring simultaneously. We've defined Bayes' theorem as the reorganization of the conditional probability. If I want to quantify the probability of E1 given A, is going to be re-expressed as probability of A given EI times probability of EI divided by probability of A. So in this is going to be my likelihood, this is going to be my prior, this is going to be my evidence, and this is going to be my posterior, okay? We're going to come back to this in great amount of detail in module 3. Then we saw the concept of random variable, for which we describe the occurrence using PDF, probability density function, CDF, cumulative density function, PMF, probability mass function, or CF or CMF, cumulative mass function. So in the case of the multivariate normal, we see that the bivariate case is described by the expected value, the standard deviation, as well as the correlation coefficient, okay? In all cases, even if we define the joint occurrence of multiple random variable, we're going to represent this by a multivariate PDF or PMF, which is always greater or equal to 0. And in a continuous case, if we integrate over all possible dimension, the outcome of that integral must always be 1, okay? In terms of conditional probability, we can say that in the case where x1 and x2 are statistically independent, it means that the conditional probability of x1 given x2 is equal to the marginal probability of x1. Why? Because if they are statistically independent, knowing about x2 won't change my knowledge about x1, okay? In the case where x1 and x2 are statistically independent, I can represent my joint PMF for x1 and x2 as the product of the marginal. So in the general case, x1 and x2 are not going to be statistically independent. Then you can build that joint PMF or PDF using the chain rule. So n-1 conditional times 1 marginal. So we saw the concept of expectation and variance. So the expected value is going to be the weighted sum or integral of the possible outcomes times their probability density or probability. Okay, this is for a continuous random variable. In case of a discrete, we're going to replace that integral by a sum. Then we have the centered moment of order 2. This is going to be what allows us to define the variance of a variable that we can rewrite with this identity. In terms of matrix notation, a key part we're going to use is the covariance matrix, okay, that include the information about the linear dependency between pairs of random variable as well as the variance of each marginal variable. And we can reconstruct this covariance matrix by our standard deviation matrix times correlation matrix times standard deviation matrix. When we have function of random variable y equal g of x, we want to maintain the probability content between the x space and the y space. So that's why allow us to write that change of variable rules, where we say f of y dy equals f of x dx. So in many cases, applying this can be tedious. It can be complex in large dimensional space, and you cannot have this relationship maintain, or you cannot do that analytically. Okay, it's going to be too complex. So in that case, we might revolve to simpler case where that relation is linear. In such a case, you can say that g, the expected value of y is going to be equal to our function evaluated at the expected value of x, meaning a m of x plus b, because here we're going to have a linear function, ax plus b. Same thing for the covariance sigma y. The covariance is going to be a times sigma x plus a transpose. In the case where we're going to have nonlinear relationship and we want to keep that simple calculation to have computational efficiency, even if we know if it's an approximation, what we can do is in the first order Taylor expansion of that nonlinear function. In such a case, the expected value for the output of that linearized function is the function evaluated at the expected value, and the variance is going to be the gradient of my nonlinear function evaluated at the expected value times the covariance times the gradient transpose. Okay, this completes what I wanted to see with you for a review of probability theory. We're going to build on this in the next module.